Okay, so we learned how to calculate the mean. Basically, it is the sum of probability weighted outcomes. So it's straightforward to calculate the mean if you have the probability distribution table. So now then, we are going to think about another example where you become a car dealership owner. So you own a car dealership and you hire many car dealers. So you are evaluating each dealer's performance. So as an example, like say you are evaluating a specific dealer and you observe the dealer's weekly sales record in the past 50 weeks, say, which is random, I assume. And then, like according to the record, of course, the data are fake again. Say, in some week, you are going to, like the dealer sells no cars, makes no deal. And so 25 of the past 50 weeks, the dealer basically did not generate any revenue. But 20 weeks out of 15, like out of 50, the dealer made one deal each week. And 4 weeks, the dealer did better, like 2 deals a week. And in a very luckiest week, the dealer could sign 3 deals. So, of course, I simplified a lot of things. It's on kind of can be unrealistic numbers, but just let's think it as an example, and we are going to extend this example later. Say, in this table, I'm going to do it step by step. The first step is to calculate the probability. So then answer this question. It is your exercise. I'm just checking if you can do each step. So first step, what is the probability that this dealer sells 3 cars a week based on the past 50-week record? Okay, pause the video if you need more time. So the answer is 1 out of 50. So in the past 50 weeks, only once the dealer could sell 3 cars a week. So the answer is 0.02. So the answer is B, right? So once you have the probability, you can calculate probabilities for each of the outcome, right? Selling nothing, selling 1 car, selling 2 cars, 3 cars. Now it's time to calculate the mean. So this is more important. You may use a calculator or Excel. So try to calculate the mean. That means the average cars the dealer sells a week. Pause the video again if you need time. So I'll tell you the idea. We have probabilities. What you have to do is multiply those probabilities to the corresponding outcome. So 0 times 0.5. Write that down here as a weighted outcome. And 1 times 1 multiplied by 0.4. Write it down here. 2 times 0.08 here. 3 times 0.02. So you are going to get another column for weighted outcomes. So you are going to get numbers like this, right? So then, after calculating the weighted outcomes, you just sum out those weighted outcomes, probability weighted outcomes. Then you are going to get 0.62, right? So then that is the mean. So again, then you can say that this dealer sells on average 0.62 cars a week based on the past 50-week data, right? Okay, this is just a repetition of what we did, just another exercise to calculate the mean. Now we are going to put a little more structure on that. So assume that if the dealer sells a car, the profit generated by selling a car is $3,000 for simplicity, always $3,000. On the other hand, the dealer's weekly salary is $2,000. Now, as an owner, you are the owner of the dealership. So you would like to evaluate if the dealer is worth the salary, right? So comparing the profit generated by the dealer and the salary paid to the dealer, I would like to make a decision. Similar case. We would like to make a decision, but the data we have is too complicated. So at sometimes the dealer does not generate any profit, so bad. But sometimes the dealer generates a lot of profit in a week. So receiving $2,000 but generating $9,000 as a profit. So then, as you can expect, it's a problem of weighting, which is more likely to happen. So which side dominates, like whether like poor performance or better performance, which weighs out the other side. That is again, it's equivalent to calculating the mean. We would like to summarize all these numbers into one number by calculating the average net profit, or average profit minus the salary, right? So profit net of salary. That is what we are going to do. So basically, we are doing the same thing with a little more structure. How can we do it? What we are going to do is, now the probability does not change. What I'm going to do is, I'm going to transform the number of cars into the net profit implied by the cars sold, right? So for example, so if the dealer sells 0 cars, then the net profit in that week is minus 2,000. You paid $2,000, but the dealer did not contribute at all, right? If the dealer sells only 1 car in a week, then the net profit is 1,000. So sold 1 car, generating $3,000, but the salary is paid $2,000. So that is plus 1,000. Similarly, selling 2 cars implies plus 4,000 profit, and selling 3 cars implies plus 7,000 profit, $7,000. Okay, so then this is transformation of the outcome, right? Put it this way. What I'm doing here is, say, the underlying experiment here is we are randomly choosing 1 week from the past 50 weeks, right? And so far, the chosen week, like we choose a specific week, and we describe the week using the number of cars the dealer sold in that week. That was the outcome. That was the numerical description of the outcome, right? The numerical description of the randomly chosen week, randomly chosen record. But now what I'm doing is I am going to describe the week not by the number of cars sold, but by the net profit generated by the dealer. So what I'm doing is I'm just relabeling, like describing the same event, same outcome with different numbers, right? Say previously the description was number of cars, but now it is dollar amount, dollar of net profit dollars, right? So mathematically, it is just transformation of the numerical description, or casually speaking, it's just recalculating the outcome. And also, what you can see from here is I did not change the probability. Basically, the random experiment is the same. We are choosing random week from the past 50-week records. So we randomly choose 1. So that does not change. The underlying experiment does not change. So the probabilities don't change. As I said, it's only a matter of labeling, encoding, a description, right? I am just changing how to describe what you choose. And then think about this. The probabilities are the same. What changed was now the outcome. The random variable changed after transformation, transforming number of cars into the net profit. So we get another numerical description, which is another random variable. However, the probabilities don't change. So there is another random variable. The transformed random variable has the same probability distribution as the original one, which was number of cars sold. Okay, now then, try this. Determine, using this transformed random variable, determine the expected weekly net profit generated by this dealer. Okay, so another exercise, basically you are going to do like, weighted outcome, calculate weighted outcome and sum them. That's what you are going to do. So do it by yourself. Do the algebra. Okay, so resume, pause and resume this video when you are done. So let me, like the procedure is the same. We are going to multiply net profit to probability and write that down here. And repeat that for each outcome. And then you are going to get these numbers. And finally, you get the average weekly net profit, right? By the dealer. So it is minus $140. So that means on average the dealer is like actually incurring a loss to you. Like each week he or she is receiving too much salary than the actual profit he or she is generating, right? So again, the procedure is pretty straightforward, like kind of automatic, mechanical. But what I want you to realize here is what you are doing is you are summarizing a lot of numbers into one number so that you can make an easier decision, right? It's clear how you make the decision. I will fire this dealer or cut her salary based on this summary of data, right? Based on this data, based on this measure, I think the salary is too much. Okay, that is what we are going to do. And another technical thing here is we are now going to study a transformation of the variable. So its intuition is clear. We are just describing with different numbers by manipulating the numbers. So we are going to study a few properties and what happens with that transformation. Right? So think about this. And this kind of transformation is pretty common. Like, for example, you have data from Europe. Then they must be, like, say, economic data from Europe must be in euros, measured in euros. Then you need to convert those numbers back to dollars using an exchange rate. Or sometimes, like, inches, measured in inches need to be converted into measures in meters. Similarly, like, say, the prices in the past must be must be converted to the real prices using considering the inflation rate. Like, there are numerous examples where the data is given, but you need to process the data, to have what you actually want. So we are going to describe that case using this way. Like, x denotes the original random variable. So x is the original random variable, and y is the new random variable you want to have, and then the transformation will be described in this way. So if you input x, the original variable x, this function g gives you y as an output. So g is the function that transforms the random variable. So in our example, x is the number of cars. If you input the number of cars into this function, and the output of the function is the net profit. It was clear in our example how to calculate that. So the relationship, the function, transformation took this form. So for each car, the dealer generated $3,000 profit, but as a lump sum, $2,000 is paid to the dealer as a salary. Okay, so this is a general mathematical notation to think of the transformation. Then how can we calculate? Now then we'd like to think about the mean of the expected value of the new random variable. How to do that? The safest way is just following the definition. Transform the random variable using the relationship. You know, just convert and then assign probability. And this is not difficult because the probability to y is the same as the probability for x, right? So probability does not change. It is just changing the labeling, right? Label description of the outcome. And then once you have outcome and the probability, you know how to calculate the mean. Calculate weighted outcomes and sum them. That's the mean. That is that is the fundamental way, the most safest way to calculate the mean. Well, of course, what we are going to do is we are going to study the relationship between the original variable's mean and the new variable's mean. So this process is complicated. It may take time if your data is more complicated and the conversion is more complicated. But what happens if you happen to know the original variable's mean, right? That could be available in the original data, easier to calculate. Then can we just utilize this to calculate the new variable's mean? The answer is no. There is no general rule. They cannot be. It does not imply any information about the expectation y. Mathematically speaking, in general, this is not allowed. But as we learned, like special multiplication rule, special addition rule versus general multiplication rule and general addition rule, we can think about special cases where they have some nice relationship. That is this case. Our case actually is one of the satisfies the special case. Think about this. Earlier, we calculated the average number of cars the dealer sells per week. That was 0.62. And just let's just assume that this is the number of cars the dealer sells, and then you can plug that into the relationship. The profit calculation is like this, and then you are going to get the same expectation. Okay, so if the dealer sells 0.62 cars, then this is the generated profit, and still this is the salary. So the average profit generated by the dealer per week is the same result, exactly minus 140. This is also true. This works. This is possible. This is exactly what we wanted. We already calculated the average cars sold, and then can we utilize this to calculate the average of the new variable? In this case, yes. Using the relationship and using the original variable, original average. This is possible because the relationship is linear. That is the point. So the conversion from number of cars to net profit is purely linear, multiplying something and subtracting something or adding something. It's a linear transformation. Is pretty simple and mathematically well behaved. So we can exploit the original average to calculate the new average. That is generalized like this. So we say x and y have a linear relationship if y can be written as x multiplied by some constant plus another constant. In our previous case, 3000 was multiplied and minus 2000 is added, right? A was 3000, B was minus 2000. And then, so if this linear relationship holds, then the new averages also satisfy the same relationship. Okay, the point here is this is a special formula. This works only when the relationship is linear. So examples of nonlinear relationship is like this. Say, for example, quadratic term, if you include square, then of course it's not linear. It's squared. And if there is a jump, say for example, y has a jump when x changes from minus to plus, right? For negative x, it is 0, but when it is positive, then it becomes 1. So it looks like this jump. So it's not linear. And utility function is another example. So concave utility function is, concave like this. It's a marginal utility is diminishing over time. That is also nonlinear. So in these examples, this formula does not work. So you have to keep that in mind. But if you are lucky to have a linear relationship, if you're lucky to show that, if you can show that, then there is a shortcut. That's what we could find. Okay, so we are going to apply this idea with another example. So in the next video, I'm going to explain the difference between linear relationship and nonlinear relationship, and we will utilize this formula to calculate the mean of a transformed random variable. Okay, thank you for watching. See you later. Bye.